So last class we talked about a preconditioner called incomplete factorization preconditioners. It is one of the most popular and well-known preconditioners when you don't know anything about the physical problem that you're trying to solve. So it's sometimes we call it an algebraic preconditioner. And today I want to talk about parallelization. So this is a high performance computing aspect. How to parallelize, in particular, the solves with these triangular factors that come from the incomplete factorizations. Okay, so I'll say a little bit later on in this lecture about how to parallelize computing the incomplete factors, but I will focus this lecture on how to parallelize the triangular solves. So if you remember, the ILU factorization produces a sparse lower triangular factor, a sparse upper triangular factor, and we need to solve with these factors at each step of the iterative method. And what we would like to do, because we have to solve with these factors over and over again, is to find a way of solving with these factors efficiently in parallel. Okay, so the focus today will be on parallel sparse triangular solves. Okay, so let's consider first a very simple problem that comes from this grid. Okay, so a very simple grid, 3x3 grid, using the natural numbering. Okay. And then let's consider that we have a sparse matrix from this grid, and we compute the ILU 0 factorization from it. Okay? So that's going to give us a sparse matrix. Let's consider the lower triangular factor, and let's consider solving with it. So the ILU 0 factor, in other words, no fill. Okay? Okay, so this is the lower triangular factor without any fill. You can see it's just the lower triangular part of the matrix that comes from this grid. Right? And we want to solve, let's say that the values that we want to find, x1, x2, x3, all the way up to x9. And the right-hand side, which is given, let's call it b1, b2, b3, all the way up to b9. Okay, so we're given the right-hand side vector. We've just computed this factor, and we want to apply the preconditioning operation by solving with this factor, and we want to compute these x's. Okay? And the question is, how do we do this in parallel? Okay. So in the first step, now we're just going to use the standard forward substitution algorithm. And there is some parallelism because the factor is sparse. Okay? And I want to see how to figure out where the parallelism comes from. So in the first step, we're just going to compute x1 by solving this first equation. Right, we're going to solve A11 x1 equals B1. Right? And in the second step, we're going to solve A21 x1 plus A22 x2 equals B2. Right? But there's another variable that we can solve for in parallel. Right? Do you see which one that is? Which variable can we also solve for in parallel along with this? Because we have already computed x1. Any volunteers? So it's not x9, because to compute x9 we need x8 and x7, which we don't have yet. This is an important step for you to see before we can continue. That's why I want to make sure everyone can see it. Anybody not see it? If you don't raise your hand, that means I can call on you to answer the question. Yeah. Okay, so it's x4, right? So x4, because x4, the equation for x4 is a41 x1 plus a44 x4 equals b2, equals b4, right? And because we've already computed x1 in this previous step, we can move that to the right-hand side, and we can solve for x4 directly at the same time as x2. So the important thing to note is that these two can be done in parallel. Okay, and how about the third step? Which ones can we compute in parallel in the third step? We've already computed x1, x2, and x4. Yeah? x3 we can compute because x3 only depends on x2, and that we just computed that. x5 depends on x4, we've computed that, and we've computed x2 as well. And there's actually another one, x7, because x7 depends on x4. Right, so maybe it'll help if I write down these numbers. So in the third step, x3, x5, and x7 can be computed in parallel. Okay, and then we can continue, and you'll see that we need how many steps? We need 1, 2. How many steps do we need? We need 5 steps to compute all of them instead of 9 steps. Like if we were going to compute it sequentially, we would take 9 steps, but we can actually compute it 5 steps, and there's some parallelism. Okay, there is, if we want to look at this generally, there is a dependency graph that we can define. of what can be computed. So for instance, in this example, x1 does not depend on any others. Right? x2 depends on what? It depends on x1. And you can tell by just looking in the row of x2 and seeing what non-zeros are there. So there's a non-zero here in the first column, so it depends on x1. And similarly, x3 will depend on x2. And x4 will depend on x1. Okay? So in general, xi depends on xj if aij is not equal to 0 and j is less than I. Okay? And to find the dependencies, of xi, look in row I. Alternatively, you can say, well, if I've computed xj, what might I be allowed to compute? Alternatively, if xj is computed, then a dependency of xi is satisfied if aij is not equal to 0 and I is greater than j. And to find these, you look in column j. In other words, we've just computed xj, and we want to check maybe now some other ones can be computed, right? So suppose we just computed x5, and then we look in this column and say, well, maybe 6 can be computed, maybe 8 can be computed, because x5 was a dependency of these other two. Okay? So the matrix, which then you can also imagine the graph of this matrix, which we're actually going to draw in a moment, tells us something about what things can be done in parallel. So here's some notation. So I'm going to draw uj with an arrow to, no, not uj. I'm going to just draw I'm just going to draw j with an arrow to I. Oops. J with an arrow to I. Okay, so this means that uj is a prerequisite of ui. And the direction of the arrow means something like the direction of the computation, right? We have to compute j first, and then we can compute I. Direction of arrow indicates direction of computation. Direction of computation is not really a real term, so I'm going to put it in these quotes. Okay. Now, if we use this arrow notation, I can say, well, here's node 1. We're going to do that first. right? And it's a prerequisite of two things, 2 and 4, right? So 4 depends on 1, 2 depends on 1. Alternatively, 1 is a prerequisite of these two. And similarly, 2 is a prerequisite of 3 and 5. And 4 is a prerequisite of 5 and 7. And we can keep going. 3 is a prerequisite of 6, and 5 is also a prerequisite of 6. 5 is a prerequisite of 8, and 7 is also a prerequisite of 8. And 6 and 8 are both prerequisites of 9. Okay, so this is the dependency graph for this example. It's a little bit different than the graphs we drew before because there are arrows on the edges. And when there are arrows on the edges, we call it a directed graph. Okay? And this directed graph is the graph of the lower triangular matrix. Okay? So this is the graph of this lower triangular matrix. So non-symmetric matrices have directed graphs. Okay, so what does that mean? It means that aij not equal to 0 in the matrix implies that there's an edge in the graph from j to I. And I'm going to ignore the diagonal of the matrix, so I is not equal to j. And we always have, for a lower triangular matrix, I is greater than j for a lower triangular matrix. So let's go back to this grid. And I'm going to draw it a little bit bigger. So this grid over here, this 3 by 3 grid that the problem came from, you can see that the graph in this case, because we have a matrix that comes from no-fill factorization, the graph in this case looks a lot like the grid. Okay, so maybe this is not surprising. Let me draw it a bit bigger. One, 2, 3, 4, 5, 6, 7, 8, 9. That's the natural numbering. Right. And we took a number of parallel steps. In the first step, we solved for the first node. And in the second step, we solve for these two nodes, 2 and 4. And in the third step, we solve for 3, 5, and 7. And then 6 and 8, and then finally 9. So these nodes that are in the same, that can be computed at the same time, are sometimes called a level. Okay, so it's different from the word level and level ILU. Level is reused over and over again with different meanings, but here we also call them levels. Sometimes for regular grids we call them waves, but here this is level 1, level 2, level 3, level 4, and level 5. Okay, so you can see there's a connection between here and here. But here we didn't draw any arrows. Okay, and here we did draw arrows. And the arrows, the direction of the arrows is important. Okay, so the edges, okay, we should really draw the arrows. So I'm just going to redraw this on this side. And the arrows always point from the low number to the high number. Okay. So why do the arrows always point from the low number to the high number? There's a very simple explanation. It's because we're in a lower triangular matrix, right? All of the non-zeros have to have this form I is greater than j. Okay, so if we have the sparse matrix, we can draw its graph, we label the arrows, and then it automatically gives us the dependency graph. So for this example, the triangular solve can be done in 5 steps. Let me call it 5 levels to be consistent. Okay. Each step or each level has to be processed sequentially. In other words, one by one, in order. But within each level, the work can be done in parallel. Each level can be done in parallel. Okay, so this was just a very small example, and let's try to look at some more interesting examples. Suppose that we have this graph, 1, 2, 3, okay, and all of the arrows point from the low number to the high number. So this is just a 3 by 3 matrix, right? How many levels are there? 5 levels? No, for this problem. If we were to solve the triangular factor, how many levels are there? In the very first step, we can solve with 1. We always have to start with 1, right? Or we could possibly start with some other ones, but here we at least have to always start with 1, right? And then in the next step, we can do 2. Can we do 3 yet? We cannot do 3 yet because we have 3 depends on 2. And then in the third step, we do 3. So we have 3 levels. And what's the size of each level? We could only do one thing in each level. Okay, and in fact, if you draw the matrix that corresponds to this, this is just that matrix. Right? There's nothing special about this matrix. That's the graph. 3 levels. There's no parallelism really. Okay. Okay. So a slightly more complicated example. Let's take So this is 1, 2, 3, 4. Here are the arrows. Okay, so it's a 4 by 4 matrix. How many levels are there here? There are 3 levels. I see a lot of people mouthing 3. And what's the size of each level? The first level has size 1. The second level has size 2. And the third level has size 1. Okay, let me change the graph a little bit. Let me erase this edge. Okay, so now how many levels are there? 3? Just like before, right? What's the size of the first level? The size of the first level is 2. We can actually do 2 things in the first step. We can do 1 and we can do 3, right? And then at the next level, we can do 2. We can't do 4 yet because it depends on 2, and then 4 is on the third level. Okay, so that gives you maybe some more intuition behind this concept. All right, now let's do a problem in which I cannot draw the graph. So suppose we have a grid that is 100 by 100. Okay, and we're going to take that structure and take the lower triangular part of that structure. And so here's another example, 100 by 100 grid, natural ordering. In other words, it's the big version of this. Okay, so how many levels? You have to imagine the grid in your head and then you count them. You can also just generalize this to a larger picture. Who says 200 levels? Who says 199 levels? Who says 201 levels? Okay, so it's 199 levels. And what's the size of the largest level? $200? $100. Okay, so the largest level has size 100. The first level has size 1, then the next level has size 2. It's a very regular problem, unlike these two. Okay, so here's another example. A 100 by 100 by 100 grid, natural ordering. It's a little bit harder to think of what the answer is. In fact, I don't know the answer. I didn't think about it. But you could also ask yourself how many levels there are and what's the largest level. You can see that the number of levels is quite large. And each level has to be done sequentially. Okay? And the most number of processors you can ever use at one time is 100 for this problem. Okay? And even if you increase the problem size, you don't really get more parallelism because the number of levels will increase when you increase the problem size. Okay? So there are some ways of getting around that, which we'll see in a moment. Okay? All right, so you might want to think about how to determine what the levels are. So if someone gives you a matrix, what are the levels? And what I did was I wrote a program to do that in MATLAB, which I've posted on the website, and you can download it if you like. It's a MEX file, but I'll just show you how it works. Let's look at the MEX file first. I guess I need the screen on. remote screen. Okay, so there's a file called lev.sch.c, and it's a next file. So you can see that there is a gateway function. So there's a gateway function called max function, just like before, and it takes a number of parameters. It's only going to take one parameter, right? And then it's going to allocate some working arrays. And then it's going to call a function that will determine the level structure called wavefront. And after that, it's going to print the number of levels. The first node of the first level is this. And then it's going to print the size of each level. Okay? And wavefront is going to, you see it takes a sparse matrix, but not the values, just the I, J, and JA, right, since it's MATLAB's compressed sparse column format. And then it's going to output the number of levels, a pointer to each level, and also a reordering vector. I think it's a reorder. Well, we'll see. Let's look at the code for wavefront. So here's the wavefront function. Okay, so P is like a working array. Not a working array. P will return all of the levels in order, all of the elements in order. Okay, and the code is posted so you can see how it works, but you can also try to think of how you would write such an algorithm. And it turns out that you want the matrix in a column format because that makes it more efficient to look at, to compute this level structure. Okay, so to demonstrate how it works, I'm going to generate a matrix which is the 100 by 100 by 100 grid. Okay. And then I'm going to look at what is the number of levels and the size of each level. So let me look at the lower triangular part. We can look at the matrix because it's quite large. It's like a million rows, right? Maybe I should do a smaller example because it's taking a long time. All right, let me try. Whoops. So 10 by 10. Okay. And there's the matrix, and we want the lower triangular part of it. Okay, and then we're going to call our level schedule. Let me do this first, more on. Applied to this lower triangular factor. Okay. So this says that there are 28 levels. Okay. And this is the size of each level. 1, 3, blah, blah, blah. The last one is 1. And the largest level was 75. Does that make sense? So it's also, I think, interesting to try to see how many levels there are in some other problems. This was just for a regular grid, right? And I have some other problems that I loaded earlier from the University of Florida Sparse Matrix Collection. So I loaded a number of these. Okay. And let's take Let's choose one of them. So let's start. Can you see that? You guys can't see that, eh? Okay, so let's load. So let's start over. So clear all. Load matrices ecology 2. Okay. So this gives us this structure called problem, which you guys have seen before. And I'm going to extract that matrix A equals problem.A. And I'm going to, let's maybe look at it. Well, let me take the lower triangular part first. Okay, so that's that matrix. It's such a large matrix that it looks banded, but it looks just like a diagonal matrix, but it has a lot of structure. And then lev sketch A. So let's look at what the level structure looks like. So it has 1,999 levels, right? And the sizes of each level, they go up. So I would guess that this problem comes from a regular grid, right? Maybe a very simple, easy structure. We can try another example. Load matrices cage 13. A equals problem A. Take the lower triangular part. Run the level schedule program. Right, so this problem has 83 levels. And it's kind of interesting because the first level already has 5,000 things that you can do in parallel, right? So somehow this is a very different problem that has more parallelism. And I think the matrices are about the same size, but let's see, what is the size of this matrix? So it is quite a big matrix. It is almost 500,000 rows, okay? Any questions on this so far? So how about for, yes?
So, given a problem, say when we are trying to paralyze the problem, suppose you first need to know the structure of the needle. And so to do that before even we paralyze it, we are supposed to get the level graph first, before we paralyze it.
Yeah, before we do the triangular solves, we have to know what the level structure is.
So for each problem, we have to calculate the different.
That's right. So for each problem, we have to calculate the level structure. And then for each triangular solve, we use that level structure. And if we use the triangular solves inside an iterative method, then we do these triangular solves over and over again, and we can use the same level structure. We only have to compute the level structure once for each matrix. Any other questions? So how about for a upper triangular matrix? So far we've just seen this for lower triangular matrix. All right, so I'm done with the screen. For now. So we've done a lower triangular matrix. How about for an upper triangular matrix? Does anything change? So you can work through all of these details for the upper triangular matrix, but I think the one thing to notice is that everything is very similar because an upper triangular matrix is just a reordering of a lower triangular matrix. If we took this matrix and we ordered it from bottom to top, then it looks like a upper triangular matrix, right? And then we use exactly the same algorithms, right? We find, well, which is the one that you can do first, and it's going to be, instead of 1, it's going to be 9, right, for an upper triangular matrix. So in fact, nothing changes. We can use exactly the same codes. So the level schedule code that I just demonstrated also works for upper triangular matrices. Does that make sense? It just starts with a different node. It just starts with a different equation. Okay? And how about for parallelizing the incomplete factorization? So this is parallelizing the solves with the triangular factors. We can use the same idea to parallelize the incomplete factorizations. So let me take this matrix, okay, and I'm going to say, I'm going to put in the rest of the matrix. And now it's no longer a solve. I'm going to get rid of this. We want to compute the L and U factors that are approximately equal to this matrix. Right, so we're going to do this. Let's say we're going to do the zero fill incomplete factorization. So how do we do this? We can proceed one row or one column at a time. Right, but you can see that there are some rows, let's say we're going to proceed a row at a time. There are some rows that can be done at the same time, just like before. Right? So in the first step, we factor the first row. Okay? So nothing, there's basically, we have to start somewhere. We have to start with the first row. Then we can factor the second row and the fourth row at the same time, right? Because to factor these two, we only need the first row, and that has already been factored, right? You can see that the fourth row doesn't need anything else. These two are 0 over here. It doesn't need anything else besides the first row, right? So the second and the fourth row can be done at the same time. And similarly, at the next step, the third, fifth, and seventh, or whatever we decided, yes, the third, fifth, and seventh can be factored at the same time. So exactly the same level scheduling algorithm can be applied to parallelize the incomplete factorization. As long as we know the sparsity pattern of the incomplete factorization beforehand, that means it applies to the static pattern incomplete factorizations, but not the threshold-based incomplete factorizations. Because for those, we don't know the pattern beforehand, so we don't know how it can be parallelized. Okay, so let's write some of that down.